So my talk is about global server load balancing. There are actually two people who've been working on this. This is me and Alex Kidd from Winstar Communications, who I don't think is here today. Okay, so you will find the full content of this talk on the NANOG website. It's actually very long. I've been trying to compress it as much as I can, and you will see a very compressed version today. The purpose is basically to give you a brief description of methods known today, to introduce some new techniques we've come up with, which we think is ideal for some specific case, and to accompany this all with some analysis of the techniques, of the pluses, minuses, and some additional thoughts. If I have time, I will go and try to tell you what technique we think can be used in some specific cases. Okay, so the plan is brief introduction. Then I will remind you about LSLB technique, which is just local server load balancing and available methods there. And then I will try to go into more detail, talking about GSLB, which is global server load balancing. Okay, and then I'll try and use what we've come up with, and again, applicability considerations, conclusions, references. So since every presentation should be accompanied with a lot of abbreviations, here they are. So LB stands for load balancing or load balancer. SLB is server load balancing, and so on and so on and so on. The most important one will be RS and VS. RS stands for real server or real services, and VS stands for virtual server or virtual service. VS is to what the client established locations, and RS is to what the connection is eventually established. So the real server that processes this connection or session request. I will try to avoid using word VIP here, because it already has a lot of meanings. And another very important thing is this right bottom corner, this ASP, CASP thing. Okay, if you ask me what ASP is, I wouldn't answer, because there is a lot of noise about ASP today, and there is some signal, but the signal noise ratio is really low, and therefore, I really don't want to go into that detail. But the point is that for us today, CASP, which is just I call collocation, content, and application service provider, is the organization that basically owns the data center or the set of data centers. It may be a customer of the ISP, and it has its own customers. And CASP is usually our customer. Our means the part of the Nartel I'm from. And our part of the Nartel has recently been called AIP, which is application infrastructure provider, which is the infrastructure means network infrastructure. Therefore, too many providers here, and if there is a time to introduce a new term like XYP, I don't know, but it's definitely time. So the logic between the recent interest to GSLB is that this CASP thing, okay, can be thought as an evolution of old style hosting, web hosting. Okay, this evolution introduced some requirements to the data center design. And these requirements are kind of new, but the old style requirements that I will talk on the next slide about, they hasn't been there is no ideal, this is my major idea of today's talk, that there is no ideal fit all GSLB solution. So every network scenario may require a different GSLB solution, and there is no ideal one. Therefore, before we actually can build upon something, we need to know what the something was and what techniques are there, and this is not finalized. Therefore, the industry today is trying basically to come up with some more or less robust GSLB solutions, but again, they're not existing. Oh yeah, so requirements to I'm not talking about all requirements to the data center. I'm talking about only those requirements to the data center that GSLB is just a solution for. Okay, So like imagine that your ISP is somewhere here, or a set of ISP. It can be internet, or it can be just like backbone of one ISP, and then there is this CASP who owns these data centers. Requirements to the data center that we're talking about is definitely high availability. So like it can be local, means that in the case of some local failure, the corresponding backup device takes over. Then high availability also means global high availability. In the case of the whole data center failure, the other data center picks up if there are services that are supposed to move there. And obviously the load balancing. Load balancing can also be local, which means the local servers are basically load balanced in the proper fashion, okay? And global, but global is twofold. The first thing is proximity. If you imagine client living closer in some sense, okay? Closer to IDC2 on my diagram. IDC is Internet Data Center. Then I want this client to go to this IDC2. But then in the event of like high load on this data, on some elements of this data center, okay? Maybe real servers or maybe load balancer itself. I want this client to be smoothly re-forwarded to the other data center. By the nature of currently available load balancing techniques, this high availability part of these requirements is just like a subset of currently available load balancing techniques. So if you basically implement some XLB solution, like SLB solution, so some SLB solution, then you have your HA there already. Okay, so brief definition of the whole SLB thing on the example of LSLB. So SLB can be thought as mapping of VS to a set of RSs. So basically, the function that load balancer performs is dynamically and intelligently map the request sent to VS to available and like the best RS. Okay, so how it does it? It performs basically three distinct activities. The first activity is health checking. So like, for example, you configure some set of real servers, but we really want to know what real servers are currently active and responsive. So you just like, the load balancer just like performs health checking of available server pool. It contains the pool of the currently available servers. The health checking can be on all levels and can be on layer 2, where you just like check the link state of the port connected to the server, or it can be layer 3, you ping the server. It can be layer 4, you try to establish TCP connection to the corresponding port, layer 4 port. And like even at layer 7, load balancers today are going with availability to check that the service exists. For example, sending in the HTTP case, sending HTTP gets and trying to get like /index.html file, for example, or whatever you define. After this pool is maintained and after the connection is received, the load balancer must decide to what is the best server, what is the next server. It will map the request sent to VS to what RS this request will be mapped to. Techniques here, algorithms available are round robin, old style and usual. Least connection, so like the real server with the least connection to it established will be preferred. Server response time may be measured. Real server response time. Server load, you can measure server load, and to be intelligent enough to know what the actual load on the server is. It may be CPU, like memory usage, whatever. And obviously hashing techniques. Hashing basically is for persistency, so and it's very important for example, firewall load balancing, when you want all the connections from the same client to go to the same real server. And then you forward the data, the actual data, to the real server somehow. Available LSLB technique and LSLB case are, like I believe a lot of people here like know what they are. It's like LSNAT described in RFC 2391, where you just like basically translate the destination IP address of VS to a destination IP address of RS. There is also like tricks like DSR, direct server return, where also known as like local triangle data flow, LTDF, where you do some tricks at the layer 2 and when the server replies, egress traffic goes directly to the client, actually to the first router, but like as matter. And also there is a much less known tunneling technique, which is also LTDF, local triangle data flow, but I believe not too many people here have heard about that. Anyhow, let's go to GSLB. This is the core of my presentation. So like, if you look at it, like usually every vendor, there is a lot of vendor, every vendor will have kind of combination of these like maybe two classes from this. No vendor has like everything here implemented, and this is usual. The first class is DNS based. So like the global server load balancing is based on on utilizing the DNS. The second is host route injections. Okay, so HRR. The third method is TDF, triangle data flow, global triangle data flows. And finally, there are some latest trends I will talk about if I have time. In the DNS-based approach, the idea is that a GSLB is actually the mapping between just like domain name and the local VSs. So if you can think about it, just like you have few data centers, all these data centers assigned IP addresses like from a different blocks. And what your GSLB technique here is trying to do is it's trying to intelligently resolve the same name corresponding to locations in different data centers, where the same basically VS existing. Okay. Like, what is the idea here? Idea is extension to some DNS. So like you need to know what? You need to know load and availability. DNS doesn't know about the load and the availability on either virtual servers or like real servers. And you have to exchange this information globally between the data centers, between the different locations. Therefore, it leads to like load report protocol, we will call it. So like some protocol, it's like every LB vendor like has come up with its own protocol. It's proprietary usually, and by means of this protocol, this load information is exchanged between the data centers. Okay, all locations of load balancers. Okay. And then obviously you need to know the proximity information, or just like proximity in the sense that in this sense. So you want to guarantee that the client has the fastest response from the server, from your data center. Okay, and you want to exchange this information also. Therefore, it leads to proximity report protocol. Usually, these two protocols are combined in one and called differently in every vendor case. And how it's done, like the load balancer is usually implement some DNS functionality. It can be just a DNS server functionality, or it can be DNS proxy or caching DNS proxy, or it even can be just like transport a DNS proxy when load balancer changes the DNS traffic on the fly. So like LPRP operation is very simple. It's just like periodical updates or request and updates or something like that between the data centers. So like here we have data centers. There are those load balancer in them, and then just like talk this protocol between each others. The transport by which this LPRP is maybe implemented. LPRP stands for load and proximity report protocol. Okay. It can be over UDP, it can be over TCP, it can be even over HTTP, and like it varies from vendor to vendor. What differentiates vendors now is what exact information is exchanged into those protocols. What kind of information is carried, okay, and how they just treat the proximity or load and load on what. So in proximity case, it can be everything. It can be delay, packet loss, some effective bandwidth. Or in the large router vendor case, it can be number of hops, number of IS hops, or even IGP metric. But again, I won't go there. What we need to understand here is that proximity in the DNS-based solution is measured not between the client and the server. It's measured between the client DNS, client local DNS server, LDNS, and the server. Okay. The load part of this LPRP exchange can be, again, a lot of things. It can be health of the actual virtual service, because like there are some entity somewhere over there which checks if VS exists in this data center and if VS exists in this data center, okay, if it's up and running. So it can be VS health, it can be VS load, so what kind of load current, what kind of current load given virtual service experiences right now. Or it can be load on the whole load balancing device, okay, so, and also there are some additional things here like load on the actual real server or network load, and another major load balancing vendor who was bought by major router vendor is like introducing this idea on how to do like intelligent load balancing, even exchanging QoS and security information, okay. So how it works? So just like imagine what I have just talked, that you have like 3 data centers, and all these 3 data centers serve the same virtual service, which is geographically distributed between these 3 data centers. For simplicity, only in one of these data centers the authoritative domain name server ADNS is located. Okay. Here we will have just like root DNS server somewhere, and then we have this customer location where the local DNS server is placed. And when you go to the vendor's website and like look at the diagrams, they will put this client into this customer location. So they assume the proximity between the client and its local DNS. Okay, this assumption is valid in some cases it's not. And let's see what's happening, how this all works in just like under the like assuming that the proximity between the client and its original location is not true. So the initial like setup is going as usual. Client requests for name resolution of some specific for some specific A record. LDNS contacts RDNS for an S record of ADNS. RDNS replaced LDNS, and LDNS goes to ADNS. ADNS is load balancing device, okay, for today. So and it talks to all other data centers and already knows the load info, so that LPRP protocol is running and the load info is exchanged. Therefore, if we wanted just like to base our decision, our load balancing decision only on loads, then we can reply right now back to the LDNS and like everything is over. But we want to calculate dynamically the proximity between the available virtual services in all these 3 data centers and the client, assuming that the client is in the customer location to your right. Okay. So what do? We just like send a request. It's part of PRP protocol to other data centers, to all other data centers, asking them to measure the proximity information to what? To LDNS, because this is only that we know at this point. So all our other data centers are requested to perform reverse pinging or whatever else activity they can like do, and then this information is collected and reported back to ADNS. And ADNS at this point know everything about both proximity and load. It can report this proximity. It can make the load balancing decision based right now on both load and proximity information. It replies back to LDNS. LDNS replies to the client, and client can now establish connection to where? To the data center which is closer to the LDNS. That is to IDC3. Okay, while the client itself is located somewhere else. So you see that as soon as this assumption about the proximity between the client and customer is not hold, the whole method breaks absolutely. Okay, and may even worsen the situation. Okay, but at this point, some vendors will tell you, some vendors that no, We are measuring the proximity between actual servers and the client, because here right now the connection is established between the client and this IDC3. The data is exchanged, and therefore the client can measure this information dynamically. Okay. I mean the load balancer in the IDC3 can know the actual proximity information to the client, to the actual client. But unfortunately, since the DNS worked before, we don't know that this client actually was bound to the request sent from this LDNS, right? So what vendors do, they do not store proximity information per IP address, either /32. They store the proximity information factorized by some prefixes like /20. And then they can guess that, okay, so if I receive the initial request from this LDNS, located here, and if the customer client is also located here, then I will hope that the client will be populating the same proximity, the same entry in the proximity database, and therefore I will learn the actual proximity information to the client. But in our case, client is remote from its LDNS, and therefore you wouldn't be able to associate this client IP address with the IP address of its LDNS at all. Therefore, you wouldn't be able to populate any, except maybe wrong, proximity database entry in here, because like load balancer in the IDC3 at the next step reports this proximity information to the proximity database holder, which is in IDC1 in our case today. Okay, like pluses obviously are those that as soon as you implement the load report protocol, you know the accurate load info. As soon as you measure the proximity in such a way, you know the correct and accurate proximity like information, but you know this proximity information not to the client but to the client local DNS server. Okay, and this is the major problem, because like it seems that DNS is like to be on target here. So you just like you try to load balance the data, but you're just like trying to do this with the help of some service DNS, namely, that is there to resolve names. So like you're basically doing like some tricks here. Okay. Anyhow, the major like minuses again that we assume the proximity between the client and local DNS, and like this is not always true. It's true only in like 60% of the cases. And also like there isn't like caching, the DNS caching. Like this information can be cached by both the load balancer if it's caching. It can be cached by local DNS, and it can be like sort of cached by applications. Application will have to be restarted to request the address resolution again. Okay, it's rather complex because you have to implement a lot of things. You have to write a lot of code for this. And like from the operator's standpoint, it's really hard to configure. And to find optimal, like I would say, it's really hard to find optimal parameters for that. Host route is much simpler, and I will like spend a minute on it. It's just saying this. Okay, you have virtual server in this data center, you have virtual server in this data center. Let us do inject host routes here and here for the same VS. VS IP address is the same. And you just like eject, advertise like through either BGP or IGP, like it's better to do it through the BGP. And you just advertise this information from different locations. Then your proximity tool is your routing protocol, BGP for example. And your load is not known until you implement some lightweight load report protocol. So the pluses here, it's really simple. It's much simpler than DNS. You do not need to write any code. Proximity is handled by the routing, load handling, as I've just said. But the like minuses are obvious. You really cannot eject host routes into anywhere except your own backbone. Even if you do inject host routes into your own backbone, you can inject them like, because if it's huge data center, it can be thousands, even tens of thousands of customers. And then you have to inject thousands of and 10 of thousands of host routes. It wouldn't work. And it's less accurate load and proximity info in the sense that BGP is not a proximity tool, okay? So like it's like, okay, it's a big discussion, but BGP is definitely not an ideal proximity measurement tool, okay? And until you implement load report protocols, you can react only to your local load, to the load on your local servers. Okay, and the most important problem is route flapping. A TDF is actually some add-on. Triangle data flow is some add-on to help you to overcome this. Imagine that client established connection to some wrong data center. Okay, wrong. I don't know how it comes. It's wrong, but there are some situations that it's unavoidable, especially in DNS-based cases. And then, like, what you're trying to do, you're trying to play some tricks and to forward this ingress traffic to the right data center, because here you're intelligent enough in IDC1 to forward it to the right data center, and the right data center then replies directly to the client. Like this bottom line is thick because if it's HTTP traffic, then the 90% of HTTP traffic is egress traffic from the data center to the client. And this is important, this shortcut. Like there is no pluses here, just like to help you. It just like goes with some addition to some other techniques, and I would say that there are some vendors they're just like base their GSLB solution solely on the TDF. I'm not trying to convince you that it's bad. Unfortunately, it's broken by source IP address spoofing. Like prevention techniques. So on these two legs, on this leg, on this horizontal leg and bottom leg, the source IP address of the packet usually is just like not point to its original source, and therefore may be broken by some things. Okay. Latest trends are those that like I would refer to go to, like, if you're interested, go to like Hydra GPS. I'm trying to just like I was trying not to name vendors, but here it would be interesting. Try to go to Hydra GPS or Speedera, and you will find absolutely hilarious ideas there. But they are very radical, you know, and I'm not talking about that. Very briefly about like our method. It's usually like really it does this. It like tries to overcome the major problem of the host route injection technique, which is host routes injection, by injecting not the host routes but the whole block of virtual services of the block which was reserved for the virtual services that are to be load balanced globally. Okay, and in the case of the local failure, it uses a triangle data flow to overcome this. So how it works? It works really simple. You just like so here you have ASP realm is here. ASP realm is here, and ASP owns these two data centers. ASP doesn't have any connections, any private connections between these two data centers, which means that it doesn't have its own backbone, because backbone in our case would be just like link between these two data centers. Okay, for ASP. ASP connects to the internet through ISP1 in one location and through ISP2 in the other location. Okay, so it obtains PA blocks from ISP1 for IDC1 and another PA block from ISP2 for IDC2. But it also obtains a PI block for those virtual server IP addresses that are to be globally load balanced, and it advertises them from both locations. Please know that since it's hundreds, thousands, or even tens of thousands of routes in there, like in scenarios of major CASPs, this will not be filtered. Okay, so this can be like the prefix can be /wanting or even shorter. Okay, therefore these two data centers advertise these virtual server IP blocks, and when the client tries to establish location, the location is established to like to the data center that in BGP sense closer. Okay, Now, if the whole data center goes down, or if the load balancing device that advertised this v/20 block goes down, then obviously, the advertisement stops at the second data center, and the client goes smoothly to the other data center. Okay, but if the local server fails, then advertisement doesn't stop because the load balancing device is still up, and we use tunneling TDF, so we establish tunnel between these two load balancer, and we forward this traffic to the other location over this tunnel. Okay, then the client replies back then the server replies back directly to the client. Okay, so like you will find all the testing information on the website, which is in the references. I will not go there. Basically, analysis of this technique is can be said briefly. It can be said that we believe, and like we may argue on that, but we believe that for this specific case, what I have just described, for the CISP that owns few data centers that are not interconnected and that are actually connected to different ISPs in different locations, this case is ideal for today. Like, not ideal, sorry, but it's probably the best than any other technique. Okay, like I had in my presentation, like the discussion of the problem how we solve route flapping. Unfortunately, I don't have time for this, but you may go to the website and figure out how we do this, or like you can download just this presentation from the NANOG website and to see that and to see how it's done. Okay, so like for testing we just like used unfortunately Linux, but the Linux was almost ready. It had Zebra, it had tunneling interface support, and it had LVS code. LVS stands for Linux Virtual Server. This is load balancing code for Linux. Okay, so just like conclusions, let me go briefly to conclusions to skip all that. So again, today you really have, if you need some GSLB, then you really need to figure out what kind of network scenario you want this GSLB to use in. Okay, there is no ideal case that will fit any other case, that will fit any case. There are some ideal network scenarios, and some vendors will be trying to convince you that they have some ideal solutions for these ideal cases. These ideal cases are really like ASP that can go directly to the client edge. It's like one of those latest trends. You really cannot produce the ideal GSLB scenario until you can control the client. And therefore, like one of the most extreme solutions is just like to go directly to the client and to modify either the client LDNS behavior completely, or just like to go just to the client application, and to utilize, for example, SRV records invented by Paul, I believe. Okay, so but for realistic network scenarios, as they are today, for like the usual standard web hosting, there are some solutions that are briefly improving. It's a very it's a good competition around there, and it's really interesting like to do that stuff. Unfortunately, since it's like so hot, we lack the testing like in the production like environment, unfortunately. For example, like the main problem is we don't have any data on how worse the BGP proximity measurement and PRP proximity measurement are. We cannot compare them. There are some references. Okay.
Thank you, Dmitry. Next is, I'm sorry.
Next is, there's
You
one
have a question, Dmitry?
Actually, it's partly a question and partly a pointer for you to some data. As part of some testing of Masataka Ota's proposal for an Anycast DNS route, we've been doing some performance testing against two different Anycast hosts, which are out of a Randy, out of an AS Randy Bush had in his back pocket and some address space he had in his back pocket. One of the interesting things we've discovered is that when you have a situation similar to the one you put up where ISP-A and ISP-B are both announcing a specific address range, you run into very early on situations where the performance of the one which is your chosen A route in this case has nothing to do with the available set of performance metrics because, as you noted, the BGP metrics are actually AS path length generated. So what we were running into pretty much constantly is the fact that we're going to a server that is considerably further away from us and has considerably worse performance than some of the other available servers because they are trying to reduce the load on their own networks by increasing the AS path length to this particular pseudo AS. So I end up in Brazil almost all the time because Brazil is very kind and says, I'll give you the real AS path length, where some of the other A routes will give us extremely longer AS path lengths than the reality. I think if you end up doing that, you'll end up in a situation where you're tunneling a great deal of the time if you're going to say, okay, here's the health check, and I know from the health check between ISP-B and ISP-A that in fact they would get better performance from ISP-A, so I'm going to tunnel them over ISP-A to give them that better performance. The problem with that is now you have a flow that runs between ISP-B and ISP-A, not just when you have the whole data center out or serious degradation because some servers are missing, but a common occurrence. And as I think Jeff Mogul has pointed out on many occasions, round trips are not your friend. And what you've done there then is to say to get decent performance, you are having to put in extra round trips. And that's a serious problem.
Okay. Very brief, there is a lot of points in this comment, and I would like to say first that I tunnel not always. I tunnel only when okay, well, let me be exact here. I tunnel traffic from one data center to another only when all local real servers corresponding to a given virtual service are down. So only in that case, when I receive the traffic to one data center and I absolutely cannot process it, only in that case I tunnel it to the other data center. Only then.
Then you will have poor performance for the AS path injection problem that I mentioned. The only way around it is to do the health checks and to move the flows to the correct data center to serve that particular client. So you kind of have a choice of poison here, and I really suggest that you may want to look at other solutions than this one.
Okay. Well, we might just discuss it afterwards because I guess it's long discussion. But I absolutely agree with you that BGP is not your proximity tool. It's ISP policy tool, first of all. Okay. But all you want to weigh is these two things: the currently available DNS-based techniques, okay, and the real simple thing, turn it on and go ahead.
I also agree that people should leave the DNS alone.
Okay.
Elliot Lear, Cisco Systems. So I think I dealt with some of the people in the room here when we did NetAid, and when we actually did this for about 70 data centers using DNS primarily. And I agree with Ted primarily, and with Paul, there it is. DNS are not the droids you're looking for most of this. But I think there's a qualitative difference between doing load balancing and proximity measuring for 3 or 4 data centers and for 50 or 2,000 data centers. And that in the case of 3 or 4, I don't think that your slide is representative, the case that you put forward is representative. I think in those cases that the DNS server is proximate to the client in general. And whenever you do these mechanisms, right, you're not trying to optimize for one client, right? You're trying to optimize for the aggregate flow. And do you have any data that suggests that you're right and I'm wrong?
Yeah, I have a data that says that the assumption about proximity between the client and its local DNS is true in like 66% cases.
But when you say proximate, do you mean beyond the
yes,
AS?
that if, for example, I try to factorize my proximity database by some like default slash prefix of okay, in some vendors this default slash prefix is /20, and like their assumption about the proximity of client to its local DNS factor this /20 is like there are some proprietary measurements that have been done and that show that it's also true in 66% cases. Unfortunately, it's hard to do in the production-like environment because you really do not have. How would you measure that? Okay, I will tell you how, but like not right now. The point is that I missed applicability statements because of what I was trying to say that DNS may be its ideal solution. It's a really ideal solution if you have some specific assumptions met. Okay, but in some network scenarios, it's not, and it's been understood. If you go to Hydra GPS website, you will see that maybe like this would be in future the ideal GSLD solution. I don't know, but my point, my main point today, is that definitely DNS, I think, is not ideal for every network scenario. Okay, so.